So we have office hours twice this week. We're starting our regular schedule. I have office hours today after the lecture for 1 hour in my office every Wednesday. We also have office hours by the TAs on Thursdays. They'll be in the lab where you do your labs in the undergrad lab from 4:30 to 5:30 on Thursdays. Okay. You have homework due on Friday. Another reminder. Okay. So we started looking at a demo last time, and I'm going to continue on. Do that a little bit slower. We were kind of rushed at the end of the class. We were just looking at some basic signal processing you could do in MATLAB. Some of you now have done the lab, have worked with MATLAB, and played around. But let me show you just some examples that we started looking at last time. If you recall, we read in an MP3, and we then just looked at some segment of it, and we're going to do some simple processing to it. Now, this music, when it gets read in, it becomes a sequence of numbers at a certain sample rate. And this variable, let's see. Let's see if that works. Okay. So there's a variable here. Let me run this first. Okay, we have two variables that we're working with here. One is a vector of all of the data points for the sound wave, and the other one is a sampling rate. If I type in fs here, I don't know if anyone can see that. It says 44,100. That's the sample rate. So the sequence of numbers, if you want to reconstruct the sound, this would be a value measured 44,100 times a second. So you'd want to reconstruct it at that rate. Okay. Does anyone recognize that number? Does that mean anything to anyone? Roughly? Yeah, for like CD, for example. Okay, so CD audio is recorded at this frequency. And there's actually a reason, maybe not exactly a reason for this frequency, but roughly 40 kilohertz frequency. What would that be? And what do you mean the frequency of sound that we can hear? So people usually can't hear above 20 kilohertz. Most people can't even get up that high. So that's considered the spectrum for audio, that you don't go above 20 kilohertz. And we'll learn later in this class about sampling and what it does to a signal and how you can reconstruct from it. And what you're referring to as double the highest frequency is an important principle we'll come across called the Nyquist frequency. All right, and it turns out that if you sample that fast, then you can interpolate correctly between the samples, and we'll see why. All right, so that's why the CD audio is roughly 40 kilohertz. All right. Now, what we've done here, as with last time, I can play back the sound. This is what we were listening to. Oh, is it not? Get that louder. Okay. We also can do whatever sort of math we want to it. And I have some examples here. We already last time listened to two of them. But for this first example, what I'm calling x1, I'm just going to take that sound. I'm going to multiply it by a sine wave of a much lower frequency. So if, I don't know if I can make the size of MATLAB screen any bigger. I tried a Control plus, and that doesn't seem to do it. So it's a little hard to read, but hopefully some of you can see. What I've done here is just multiply x by sine of 2 pi 1000 t. So this is a sine wave of 1 kilohertz frequency. Right, that's kind of a high note. Middle C is in the 300 range. Something is 343. I don't know. What 362 is middle C. So we're talking, we're up, over an octave higher than that, right? But when I multiply it, who knows what it's going to sound like, right? Should be something interesting. So it turns out, actually, we'll have a good way to understand what that did to the signal as we go through and talk about the Fourier transform. Because when you multiply two signals, they do something very, very simple when you look at the signal the right way in the frequency domain. Okay, so that's all stuff to come. We also, let's see. We listened to it when we squared it, but I'll do that again. And remember, I had to rescale it so that it wasn't too quiet here. So if we squared it, it did some funny things. Okay. We'll do square root. By the way, square and square root, these aren't necessarily things that are very... unlike the first example, I don't have good intuition for how to explain what it did there, except what you all already can understand intuitively, that it squared everything. We could square root, and maybe it'll sound a little different. Okay, so that's very different. Right? What was that? Let's hear it again. Okay, I'll play the clipping again. We did that last time, and just to hear the difference there, I won't scale it. Well, maybe I'll scale it. Okay. Kind of loud. All right. Now, one last thing I want to do here is take the sound vector, which I have in a plot right here, and I am going to subsample it. I'm going to just keep I'm going to throw out most of the samples, and then just keep one every, in this case, 30. So I have this number here, 30. So every 30th one I'll keep. Throw everything else away. Should lose a ton of information, right? In this plot, I actually show what that's doing. So the red dots are every 30th sample. So this is the value of our sound vector over time, right? I can zoom in and see it more carefully because 5 seconds is quite a bit of time for sound. So let's zoom in. Okay, so that's the sound wave. These points connected together with the line. And there's little red dots, a little harder to see here. There's dot, 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 dot. This is every 30th sample it's keeping. And then let's throw everything else away and see if we can listen to this somehow. Now, if we do that, we should also adjust the sample rate that we tell it to play back the sound. If we don't adjust the sample rate, this sound is going to take 1/30th the time, right? We can do that first. If I don't adjust the sample rate, and I just say sound x5 fs. Okay, that's what it sounds like. But if I reduce the sample rate here, let's do, I think I have to round, yeah, fs5. All right, so I've made a variable that's just fs5. It's just, as you can see, fs over d. So this should slow it down. We should be able to hear it correctly. Definitely doing something weird. Maybe it surprises you that you can actually still hear a lot of the sound. I mean, we barely have anything left, and yet you still hear a lot of things, but there's definitely artifacts. There are these weird sounds in there, I'll play it again, which have nothing to do with the original. Right? That note, that high note there, right? What's that coming from? It's just like, comes out of nowhere. All right, I mean, compare it to the original here. So when I do that subsampled one, it hits some like way up their note right about now, right there. Which is just wasn't there in the original. In fact, subsampling, this is something that we'll be able to understand very well through our understanding of the Fourier transform. Okay? There's a correct way to do this. So this isn't just a bogus example. Sometimes you actually do want to reduce the amount of data. It's a form of compression. There are other forms as well, but one way to do this is actually to reduce the sample rate. Okay, for example, phones do this. Okay, they don't give full quality sound, but you'd have to do it a correct way. You don't do it like I showed you, where you just keep every 30th one. There's a correct way to downsample, and we'll get to that again later in the course. And they actually have a command here in MATLAB called resample that will do it correctly. You have to process it before you take every 30th one. Okay. Now, of course, you still have a lot less. Your signal's still a lot, less numbers, right? So it shouldn't be the full quality, but at least it's not going to have the same artifacts. So here, this new thing here, I'll call it's X5 resampled, is the same length of a sequence. Let's hear how it sounds. Okay, notice that a lot of the artifacts are gone. I'll play back and forth between these two again. You hear all those artifacts that you'd rather not have. If you do it correctly. Okay, so you got rid of the artifacts. But yeah, of course, it's still not as great of sound quality. It's kind of muffled. I'll play the original one more time so you can make that last comparison. Hear the full quality sound. If you downsample by a factor of 30, you should hear a difference, and you do. You hear this muffled sound. But at least you can remove the artifacts if you do it right. All right. Okay. All right, so now we're going to begin our first foray into Fourier. What? Oh, it's my drawing tool. Okay, we talked about periodic signals, and notice that we said sinusoids are periodic. For example, let's look back at that. Suppose you take a look at cosine of 2 pi ft plus a phase. We said that this is periodic with period 1 over f, okay, or any multiple of that period is also a period. But the fundamental period is 1 over f. Therefore, the fundamental frequency is f. Now, of course, now what's the surprise here is that any periodic function can be decomposed into these. So any periodic function can actually be decomposed into a sum of cosines of this form. All right. So this is actually general enough to represent all periodic signals. So let me show what I mean by that. Here's how if you sum them up, you multiply your cosines by a scaling constant. We'll call that a sub k, and then you take all the multiples of your fundamental frequency. All right. And you give it the correct offset. Then this, with the correct choices of a's and ph's, you can represent any periodic signal. All right. So any actually needs some qualifying, and we'll talk about that. So it's not truly any, but pretty much any signal you want. Okay, it has to, yes? So it's a sum over k's. So in other words, what we're doing is we're taking an potentially infinite number of terms like this. Each one is a sinusoid of a multiple frequency of this f naught. Right? So you have some fundamental frequency and all of its multiples. And if you do the proper scaling and shifting, you can use this to represent any periodic signal. I think it's best to start with an example here. So let's pull open a little demo of what I mean. So a student in this class several years ago made this for me in Mathematica. And what it's going to do is allow us to pick a function, a signal of any shape we want. Oh, let me do this. It says aborted. How do I read? Great. Oh, Okay. I've not used Mathematica in a while, although last night this worked. So how do I rerun it? Does anyone use Mathematica here? No? No Mathematica experts? Let's see if I can. Maybe if I pick a different one. Oh, there we go. All right, it's working. Okay. So what we have here is we have a signal. In this case, it's very simple. It's just zeros, and then it's 1 for a while, and it goes back to 0. It's a little hard to see where it's 0, but where you don't see it, it's 0. All right, so this is just what we call a rectangular function, a rect. And then these other screens are going to show you how we're going to try to reconstruct. Over here, we're going to try to reconstruct the rect by adding together these sinusoids. Now, the first sinusoid that we use is the zero frequency sinusoid. It's just a constant. So the first approximation, if we don't use any sinusoids, is we're just going to kind of cut it in the middle. That's our best approximation. Pretty bad. But if we add a sinusoid, we're going to add sinusoids that have multiple frequencies that are multiples of 1 over this length. So this window length here. So this goes, as you can see, from negative pi to pi. All right. So these are just going to be sinusoids with, of the form 2 pi, or no 2 pi. They're going to be just kt. Okay, those sinusoids where k increases as I increase this number here. So the first sinusoid we would add to approximate this would be this one. Now this has chosen the correct amplitude and shift. And notice, because of symmetry, there's no shift. The best sinusoid doesn't have a shift. It's just a cosine. All right. So this plot here is showing the sum of these guys right here. The only difference between this and this is showing the sum. It's also not stopping at pi. It just continues on. Okay. So now let's find a better approximation using an additional sinusoid. So if I go up, there's another one of twice the frequency of this window. And when it adds in, it starts to look like this. Okay. The idea is that if I keep adding, now there's another one, very small. It didn't need much here, to add a little more correction. So I'm using 3. Now I'm going up to 4 times the frequency. And this one was actually substantial in size. And now if I just keep clicking here, should make a better approximation of that rect. Okay, so you see it's getting closer and closer. I can go up to some large number. I have 15 of them here. What if I go up to, like, let's say 40-ish? There's 42. It starts to look like a pretty good approximation of that rect. And the idea is if I kept adding sinusoids, I'd get closer and closer, and I'd approach it in the limit. So let's do another example. This should give us several functions here to work with. How about this one? So this is a linear function, although since I'm only going to try to use these sinusoids to match it within a window here, don't know if I said when I introduced, let's see, in the notes here, did I say that, yeah, any periodic function. So we're considering a function to be periodic, all right? So I'm showing a signal that's a straight line, but you should imagine that once it gets outside this window, it repeats, okay, because we're just trying to match periodic functions. Here we go. There we get a cosine with a shift, right? So here it actually does have to find the right shift. You see it quite quickly starts to look sort of like we expect. This is what we expect because between negative pi and pi, it's the straight line, and then it repeats. Again, if we go up to a large number, then it starts getting pretty good. Notice it has these ripple effects, and that always happens at discontinuities. Okay, there's a lot of study of exactly how large these ripples are. Notice if we drew the actual line we're trying to match, we'd go straight through the middle here. Whoops. And you could compare the peak, how far off that ripple is at its largest point. Notice it happens there on the very last ripple is the largest one. Right, so there's some peak there. So that actually never goes away. In fact, it converges to a fixed number. This is a well-studied phenomenon. And you might say, well, if it never goes away, how can I say the function converges? Right, it's always got that error there. But it's a little bit tricky. The location of that error moves. So at any one point, it does converge, except at the discontinuity, right, because it's moving. But even more importantly, there's several notions of converging when you talk about functions. All right, and what I just mentioned, that's pointwise convergence. That says at every point it should converge. And that actually, to guarantee that a function is going to have pointwise convergence, you need to be continuous and you need some extra conditions. So that's not the type of convergence we care about the most. In fact, what we care about is looking at the error between this approximated signal and the one we're trying to approximate. That error is a function of t, right? And we actually want to know when you square it and integrate it, does that go to 0? Okay, and we'll talk about that in a moment. In this lecture, what's this squaring and integrating? We call that the power. We want the power of the error to go to 0, and that's going to happen even if it's discontinuous. So even though those things, that gap stays big, it gets narrower and narrower, so it doesn't have much effect as you get to higher and higher constants. Here's another fun one. We can match even something like this. Let's give it a moment to process. Okay, so we have a parabola here. Of course, we've cut it off. So when we try to match this parabola with sinusoids, here's the collection of them, and you add them up. This is a very nice approximation of it. And of course, once it gets outside that window, it just repeats, right? Because we're using sinusoids that are periodic. Has to repeat once it gets outside. Okay, so this is the idea actually of the Fourier transform, is saying, well, let's look at a signal instead of its representation in time. Sometimes it's more interesting to say, which sinusoids did you need to compose that signal? Right? Is there any more we should do here? Triangle. So these ones are easy. I mean, with the same number of coefficients, it's looking like a much better match than the ones that had discontinuities. Right? In fact, let's see. If we went all the way down to like 20, would it still look good? 22. All right. So it needs to calculate. All right, and it updated, and you see a little bit of curving around the corners. All right. Square wave. This is like our rect, but repeated. So it should be a little harder to get. Just be patient. It'll update. Maybe. There we go. Here's the square wave. It goes up to 1 and then down to -1 and up to 1 and it just keeps repeating. So it's sort of like a rect, except the rect didn't go to -1. And here's an approximation using 20. So you can see the square wave needs a lot more a higher order approximation to do a good job, because this isn't that great yet. But if we went up here, and it's rendering. Okay, so it starts looking a little better. But we're using 60 terms in this sum. All right, any questions about that? We'll get back to the math. There we go. Okay, so something to notice here, there's a trig identity. That is the following. All right. If we have a cosine, no phase shift, a true cosine, and a sine added together, actually let's subtract just for convenience here. So we have the sum of a sine and a cosine. That can be expressed as a single sinusoid, but you have to correct the magnitude and the phase. So it equals cosine, the same frequency, minus this arctangent of b over a, plus a pi, depending on whether b was negative or a was negative. Okay. Does anyone notice a ring to this formula here? Something familiar? Let me rewrite my scribble while you think about it. Does anyone see anything familiar in this equation? I think last lecture. Okay. Maybe over here you see this type of thing and this type of thing. If you started the problem set, then yeah. Yes, so you're correct to identify this with Euler's and with magnitude and phase of complex numbers. In particular, this is just like the formula I gave for calculating the magnitude and phase of a complex number when you know its real and imaginary parts. Okay, so let's take advantage of this and notice a few things. It implies that one, that if we instead, because notice our claim is that when we sum cosines with the right phase, we can reconstruct any periodic signal. Well, that means that we could also write a sum of this form. All right, and this would also be sufficiently general to reconstruct anything, because we could just convert any shifted cosine, we can convert it to an A and a B. There's an equivalence here. So if we could reconstruct something from cosines of the form on the right, then we could also reconstruct any signal we want from cosines of the form on the left if we so wanted to. Another thing to notice is that we could encode these coefficients into complex numbers. What we mean by that is let's let CKs be a sequence of complex numbers. And we'll use the following to derive our CKs. We'll let CK equal AK plus IBK. Okay, so we'll just set AK as the real part of C and BK as the imaginary part of C. Then we get that the formula up above in 1, by that I mean this thing, okay, that equals I'm going to make this to minus here. Okay. Oh, and that's a plus. If you caught me on the trig identity, it should be a plus over there. All right. So this is equal trivially. We just substituted in what we defined. But we also can say that equals sum in terms of these polar coordinates of the polar representation of C. So it equals the magnitudes of CK times cosine 2 pi k ft plus the phase of CK. So this will be how we denote phase. In other words, just to be clear, CK equals magnitude of CK e to the I phase of CK. All right, so that's what we mean by that symbol. Okay, so now we see, a way of mapping between, this cosine with shifts versus a cosine plus a sine. All right, that's not the most important thing to take away from this. What is the most important thing is that we could use Euler's identity here. Okay, which says that cosine of 2 pi k ft plus this phase. All right. So this equals, by Euler's identity, 1/2 of e to the I 2 pi k ft. I'll get rid of the 0. Okay. Times e to the I phase ck plus the negative of these. Which equals, so therefore, okay, so that's what cosine equals. So therefore, the above, I'll just keep referring that to 1, equals the sum k equals 0 to infinity of the magnitude. So we have a magnitude of C out front, and we have, I'm going to take this first term here, and just make a sum out of these first terms. We have the magnitude of C, and we have the phase. So that's going to equal CK e to the I 2 pi k ft. Okay, that's from the first term of this Euler's identity. Let's just write another one here with a new sum. K equals 0 to infinity. And this one has, the phase has a negative in it. So let's say CK conjugate e to the negative I 2 pi k ft. All right, so there's a new way now. We could represent any signal this way. Okay. Now I have to be even more clear of what I mean by any signal. Let me go up here and add a qualifier to any. Any real signal of real numbers. Right, we're not going to be able to make complex signals with this formula here. Okay. Of course, you may be wondering, why would we want to deal with anything that's not real, right? Our measurements are real, sound files are real numbers. In real life, we have real numbers. And for example, why would we want to use Euler's identity and represent a real signal using these functions, which are not real? Okay. And there are many reasons why. Give you a couple. So why use complex exponentials, complex functions, especially if our signal is actually real? Well, for one thing, it's nice that you can simplify a lot of trigonometric identities with Euler's formula. So that's the first reason why I think it's nice to use complex functions. Trig identities are trivial. Not all of them, but a lot of them. Okay. For example, sine times cosine. You have somewhere either in your mind or in a reference somewhere what the formula is for sine times cosine. In terms of it's just a sine with a higher frequency. Okay. But you in fact can just derive that in a moment from Euler's identity. Let's just try it here. Sine of t cosine of t equals 1 over 2i e to the it. Now let's make it x just so that we're more comfortable with that. E to the ix minus e to the negative ix times 1/2 times e to the ix plus e to the negative ix. What we can do is multiply that out. Let's take our 1 over 4i out front, and we get e to the I2x, all right, minus 1 plus 1 minus e to the I minus I2x. You see that? I just cross-multiplied everything. And that means it's this. And we can identify that as 1/2 sine 2x. Now, I hope I did that correctly. It's at least close to correct. I'm just doing this on the fly here. I didn't plan on working that out, but you see how simple it is. Is that the correct formula? Yeah. Okay, good. I got some nods, so that hopefully that's correct. And you just got it in a moment with Euler. So there's one reason to prefer these complex exponentials. They're so easy to multiply. Okay, so we'll put that here. Multiplication is easy. Derivatives are easy. Of course, they're pretty easy with trigonometric functions also, but I would say there's nothing easier than the exponential function for derivatives. Okay, but also Fourier transform properties. Are simpler. This is the best part. So we could have just tried to work with sines and cosines and decompose. We could live in a world where we're trying to decompose a signal into a sum of cosines in this form. And then when we want to understand properties that we're going to be exploring throughout this course, it would be a little more like trigonometry. There would be stuff to remember. A lot of little pieces here and there that you have to remember because it just the bookkeeping gets complicated. If you instead consider a representation that we're showing is also sufficiently general, this one here, as our decomposition of a signal, then actually the properties are very simple. And one extra bonus is this can actually reconstruct. So you're not restricted to only look at real signals. So if for some reason it was beneficial, and often it is mathematically, to be dealing with a complex valued function, okay? Complex valued signal. True, there's not a good analogy to what you're measuring out of your sensors being complex. But sometimes it makes sense, like if you have two sensors and they're related in a certain way, to think of one as a real part, one as an imaginary part. Okay? So anyway, for whatever reason, if you have a complex valued signal, you also can, and it's periodic, you can represent it in this way without the constraint. So in general, you would say this becomes, these are the positive frequencies. And if you allow yourself to have the negative frequency term over here not be just complex conjugates as their coefficients. So if you allow, if you relax this and allow it to be any new sequence of complex numbers. Okay, it doesn't have to be a conjugates of the first sequence of complex numbers. Then you can represent any complex signal you want. All right. So that leads us to the actual Fourier series. So now I'm going to give you the formula that you'll be able to use. You'll use it, for example, on your problem set. Here's the Fourier series. Oops. What you have is you have a forward part and a backward part. The forward part is referred to as the analysis equations. And that is, define a list of complex numbers, C sub k, in the following way. Let's say, let your signal x of t be periodic. We're assuming it's periodic to begin with period capital T. Then do the following calculation. Do an integral 1 over t, integral from 0 to t, of your signal times this complex exponential. The frequency of this complex exponential is k over capital T. Okay, so do this integral. Now, I want to give you some intuition on what these complex exponentials are like. We're kind of low on time today, so we will continue and get more intuition next time. I'm going to give you the formulas that you can use to calculate right now. So this is an integral that depends on your signal, and you can compute any ck you want this way. The magic is that those ck's are exactly the ones you would need to reconstruct your signal. So here's the backward part is really the magical part, and this is referred to as the synthesis equations. And that says that your signal x of t will equal the infinite sum of all the k's, ck times e to the I 2 pi k over t, t. Okay, so this is basically the claim we were already making. We were saying that any periodic signal x of t can be represented somehow by a sum of sinusoids. Now, instead of sinusoids, we're saying these complex exponential functions. We know from Euler's identity they're somehow related to sinusoids. Next time we'll look at that more carefully. But we're saying that, yeah, if you scale them properly, you give them the right shifts that's encoded into the phase, then you can reconstruct anything you want. But here, what I've given you is actually the way that you would compute those coefficients. So, in the demo that I showed, where we approximated the rect and we approximated the parabola, that was just kind of magically done underneath. Was it calculated what the best coefficient would be for each sinusoid. And hopefully some of you were wondering, well, how did it calculate that? You know, how did you know what the best sinusoid would be to form the approximation? And the answer is, here's how. This formula tells you exactly how. It tells you how large to make each one, what phase to give it. Notice that this sum goes from negative infinity to infinity. Before I was always saying 0 to infinity. That's because these complex exponentials are kind of interesting. A negative frequency is not the same as a positive frequency. And so you actually need to get both parts. You need to have negative values of k in here as well as positive values in order to have flexibility to approximate any signal. And that's kind of, you could have seen that coming by looking at this representation, where we had to have a positive frequency part and a negative frequency part in order to reconstruct, for example, real signals. You would have to match these so the imaginary parts cancel. We'll talk more about that next time. And I guess you don't know yet how to calculate power and energy, and I'm not going to do it now. That is on your homework, so you'll have a few problems to finish up on Friday after the lecture.